So the question is, how do we know the linear momentum is conserved or not? So what is the condition? Okay, and it's really just the second law, but in a momentum form. So first of all, when we use Newton's law, it's in the acceleration form. It is sum of F equals to ma, and those F and A are the vectors. And if there is no net force along a particular direction, we know that the acceleration in that direction will be zero. So as a result, the velocity in that direction will remain constant. And we can create this thought process using Newton's laws in linear momentum form. That means if there is no net external force acting along a particular axis, then the component of linear momentum of the system along that axis cannot change, so it is conserved. Okay, so if it is constant, that means it's not changing, it is conserved. And again, this is a very important concept, and we will have several other conservation laws, so kind of builds on top as well. So if you understand this later on when we discuss conservation of angular momentum, it's going to be much easier. So let's consider a large water balloon which is shot through the air. We will ignore drag force. So yes, the balloon will rotate and change its shape as it flies, but we know that we can still use projectile motion equation for only one single point on the balloon, right? And that point is the center of mass point. So it's still applicable, and still we can use what we know, nothing new, and still investigate its motion. And again, the drag force is neglected, so the only force acting on it is the weight force. That's why there's only acceleration downward along the y direction, and that's the acceleration of gravity. And so there is no net external forces along the x direction because we don't see any forces, right? And we are ignoring drag. And we will apply Newton's law in both forms, acceleration and momentum form, to see what they give us. Okay, so when we focus on the acceleration form, we are here, we say that let's look at the x component. So sum of fx equals to ma, center of mass x, and sum of fx is 0. That would mean that acceleration along x direction for the center of mass point is also 0. What does that mean? That means velocity of the center of mass point along the x direction is constant. It's not changing, because that's the definition of acceleration, right? So initial and final velocities along the x direction for the center of mass point should be the same. And that's true for projectile motion, right? And that's why we can still use it here for only for the center of mass. Next is momentum form. So the momentum form, instead of ma, we have dp over dt. Okay, so that's the rate of momentum with respect to time. So once again, there are no x components of the forces, so this is gonna go to 0, just like it did here. And the right side means that rate should be 0, so it's not changing with time. Okay, px doesn't change with time. That means px is constant. The momentum along x direction is constant. What is momentum along the x direction? It can be written as mass times velocity of the center of mass point along the x direction. Since mass is already not changing, we can say that velocity along the x direction is also constant, right? So when we find out that the force is 0, net force is 0, that rate, or this one, can be written in terms of initial momentum along x direction is equal to final momentum along x direction. Okay, so this is the conservation of momentum, and it comes from second law in the momentum form. And what that means P is mass times velocity. When you write them in terms of the definition of the momentum, mass will go away and you get the same thing, as you should, right? Both of them are coming from the second law, Newton's second law, just different forms, and they should give you the same thing, and we did.